And once again, welcome you all to International Space Olympiad final level training. So this is our whole syllabus, something about space missions, space telescopes, then observatories, then important space missions, space agencies, space spin-offs, etc. So here we can broadly say that the whole topic or whole syllabus is something like one is related to telescopes and types of telescope, those things, and the other one is about space missions, like what are the rocket missions, what type of missions that we do have. And just a second. Okay, so the second part is about space missions, like what kind of satellites are there, what are the kind of space missions that usually happens. So then during that we will also discuss what are the basic kind of missions are there, and manned mission, unmanned mission, all these things. So that is about space mission and telescopes. But today I will start with the telescopes, and today and most probably tomorrow we will continue with the telescopes, and because it's also a major topic, so we will continue till tomorrow regarding telescopes, and from day after tomorrow onwards, maybe during the last 3 days, for the last 3 days we will continue with the space missions. So this is the whole plan, okay, of covering the syllabus. And as you know, one more caveat is there, something like when you hear about the major telescopes, if you want to discuss the major telescope, that is actually difficult to cover all the major telescope that are there in Earth or maybe in space. So I will be explaining only some of the important ones, but there might be questions from other ones as well. My examples will be limited because of the time constraint. But what I am planning is to give a concept of how this telescope works. And when you read more about other telescope, that reading will be easier because of this class. That is actually my plan, actually, how to execute this on this. Okay. So let's go first about telescope. As you might already know that this dish antenna-like thing is actually a telescope, which is a radio telescope. And sure, there are radio telescope as well, and we will discuss them in detail. So anyway, just given a picture that all the telescope doesn't look like what you are seeing on images, something like a long pipe or a long tube that Galileo used. So from that, telescopes are evolved even beyond, we cannot even sometimes recognize that's a telescope. That much evolution has happened in the case of a telescope. So that is why this example is given. Usually when we see this, we will see that it is something like related to TV reception or TV transmission like, but this is actually a telescope. So before going to telescope, telescopes are basically, we know that they are collecting light from the cosmos. Okay, so from the universe, it is collecting light actually, and those light getting photographed or maybe analyzed using some special instrument to know more about the universe, to get conclusions or results from those lights. Or okay, so that is the or maybe some discoveries from those lights. So basically light is what we receive from the space here. And regarding that light, especially in astronomy, when we hear the word light, it is not the usual light that we can see. So when you go outside and see, or even when you're listening to my class right now, you're actually seeing light that is coming from your screen actually. So that is that kind of light which our eyes are sensible to is called a visible light. Okay, so that is why it is always referred as visible. Visible means it is visible to whom? It is visible to our eye, human eye basically. Because other animals have some other range actually. They can also see some part of infrared sometimes, so, or maybe some ultraviolet. So anyway, human eye can detect, then that is called the visible light. So why we are specifying some light as visible? Because there is another kind of light which is actually invisible to us. Some examples are given here. This is an X-ray film. But X-ray film, when we are seeing an exposed photo of your bone using X-ray, when you are seeing this image, actually this is not X-ray. You cannot call this as an X-ray. We call it as an X-ray, that is a name given, but you are not seeing the real X-rays with your eyes because your eyes cannot see. So if you go to some, what is called, to take an X-ray or something to a hospital or a radiologist, they will tell you to be steady, something like maybe lying down or standing or something, whatever. And then they will say that it is over. You cannot see any flash that usually you see in a studio where you go for taking a photograph, a passport size photo or something like that. You will see a flash there, and you can even see that flash. Similar flashes are also happening there in an X-ray film or an X-ray, we can call it as an X-ray room as well, but we cannot see them, okay, because our eye is not sensitive to X-ray, okay, but we can convert it into a normal like photograph so that we can see with our own eyes. Just a second. Okay, sorry. Now, another example is actually radio, or maybe even now you might be receiving internet using a Wi-Fi modem is there. Usually we use that. So you won't see any signal, any real thing that is coming from your Wi-Fi modem to your phone or maybe your laptop. So why? Because there is some kind of an invisible thing is coming. That is why you are receiving my class or maybe internet or YouTube or whatever. So internet is connecting because of something is coming. That something which we usually call it as the radio waves, which is not visible to human eye. Similarly, if you go and take a photograph of some place using an infrared camera, you won't see something like this with your eye. But infrared can actually sense heat. Okay, so anything that has a temperature, whether it is high or low temperature, it is always emitting infrared. So, but we cannot see. Usually, during maybe you know that there are some kind of thermometers which is actually measure your body temperature even without touching on it. So that is actually sensing the infrared that is coming from you. And in microwave oven, cooking is happening by use of microwave, which we cannot see. So these are all examples of light which we cannot see. We, in the sense, the humans cannot see. Okay, human eye cannot see. So the examples are something like gamma rays, X-rays, ultraviolet, infrared, microwave, and radio wave. So it is arranged in a, you can see that it is arranged in something like an order: gamma ray, X-ray, ultraviolet, and between ultraviolet and infrared, a tiny portion is assigned for the visible light. And visible light is consist of those different colors, that is the violet, indigo, blue, green, that is the VIBGYOR of colors are there, and infrared, microwave. So this is in a, this order has a special meaning. That means here, this is the, here you can see energy increases. When you go from right to left, the energy of the light increases. So you can see that gamma rays are most energetic and radio waves are least energetic. Okay. Also, you can see that since light can be considered as a wave has a length called wavelength. So wavelength is the distance between two crusts or maybe the distance between two troughs. So gamma rays has a short wavelength, whether when you go for radio, it is actually long wavelength. So the wavelength is there, and there is one more quantity, that is frequency. So high energy means high frequency. So gamma ray has high energy as well. So it is actually arranged in the order of energy, maybe order of wavelength, or maybe even the order of frequency. We can call it like that. So this arrangement of different kind of light is usually called as electromagnetic spectrum. Okay, spectrum. So why I'm mentioning this, all these physics things in this astronomy or telescope class, because um, normally we can only see things in the visible light with our human eye. And when the Galileo used the telescope, or maybe Newton, or even after that before the electronic sensors and all, we all observe things in visible light only. Okay, but now we have equipments which is able to detect light in all these different wavelengths. Something like X-ray, we have photographic films already can detect many of this light, and before that, maybe before films we cannot actually detect these lights, we can only use the visible light. But after the detection, or after having technologies to sense these lights, we are actually able to have sensors is means something that sense. Okay, so has the ability to sense gamma ray, X-ray, ultraviolet, infrared, microwave, and radio waves. And what is its importance in astronomy or maybe in space? The importance is that all the sources, almost all the sources, or maybe when you are looking at the sun is actually emitting in all these wavelengths, or other astronomical sources, almost all the, from space actually we receive all these types of electromagnetic waves, or we receive signals in the entire electromagnetic spectrum, or usually we can call them together as light. Okay, so in astronomy, the light is not the usual light. We can say that when we use the term light, it consists of everything, and when we specify the visible light, that is a tiny portion, that's all. So that is the meaning of light in astronomy, because we have telescopes in all these wavelengths. So the scientists, the astronomers can actually observe in gamma rays, X-rays, ultraviolet, radio waves, infrared, visible light. All these are accessible for us. So that is the importance of, that is why I am mentioning. And based on this, we can actually classify the telescopes based on which kind of wavelength it is observing. We can actually classify telescopes. Here you can see the first example is the Chandra X-ray telescope. So this is an X-ray, and some part of the gamma rays or high energy waves will be detected by this telescope. That is the X-ray telescope. The second one is actually the James Webb Space Telescope, or JWST. So it can actually detect in infrared. This is an IR telescope or infrared. So what you are seeing on the bottom, this is something like a dish antenna, which was the title slide you have seen, the similar one, and that is basically a radio telescope. So you see, this is infrared, this is radio telescope, this is X-ray telescope, and Hubble is actually mostly invisible, but it can see some ultraviolet and some IR as well. So it can see in, if we generally say, we can say that it can see in all these three wavelengths. And this is a visible light telescope, but visible almost the telescopes like this, we will explain later, all of them are actually visible light telescope, but we usually, or astronomers don't use that term. Instead of that, we call it as optical telescope. Okay, so they are called optical telescopes, not visible light telescopes. Okay, it is optical telescope. So we have optical telescope, which then IR telescope, that is an infrared telescope, visible UV, IR, radio, X-ray. Okay, so all kind of these telescopes are there for available for astronomical purpose. That is why I explained that. So in astronomy, the light means not just the light that we usually see. It consists of many different kinds of lights. Okay. Now, what is the purpose of a telescope? So purpose of a telescope, usually when we think, we say that it is to magnify the things, okay, to zoom into the universe or something like that. Yes, initially it's a kind of a correct answer, but more than that, it has another purpose actually. So it should be able to see what is not visible for our eye, not about the infrared or ultraviolet I am talking. So just think about you are on an open space. Imagine you are at midnight and there is no moon at all. It's a new moon day and you are in a ground where it is less light polluted. And when you look at the night sky, you will see stars there. Okay. So those stars are visible to your eye because the light coming from this is reaching you, and the light is entering your eye and it reaching your retina. But there is a problem. How many stars you can see from a night sky? You will, if you see it properly, or if you start to count, it is only some 3,000 to 4,000 stars that you can see with your bare eye. Not with I'm not talking with a telescope. Without a telescope, you can only see that much. Why? Because even though there are some invisible, or there are billions of stars are there in our galaxy itself, we cannot see them because those stars are so faint the light coming, that is not enough to activate the cells on your retina. Okay, so for that, what we can do, that is our question. So if you observe our something called our pupil, okay, so the size of the pupil can actually go from this direct size, that is the least size, and this is the biggest size. Okay, it can contract and expand. Okay, you can see it becomes smaller, it becomes bigger. Okay, so it happens because if you are in a darkness or something, if you want to see more things, or in a less lighted situation, or in a dark or dim situation, if you want to see more, your pupil can expand so that the light so that more light can enter through your eye. So that is why your pupil dilates. It's a purposeful thing. So similarly, if you are in a sunny day in the middle of a ground or something like that, you need not to have that much amount of light. Actually, you need only a tiny amount of light so that the pupil will become smaller. So if your pupil can become more wider, the maximum size of a pupil for a normal eye is something like maximum 7 millimeter. It won't open that big like your mouth. Okay, so but imagine that if your pupil can be opened like your mouth to a bigger size, something of the order of some 5 to 10 centimeter, then you could have seen more stars in the sky. Even the Andromeda galaxy will be so much beautifully visible to your naked eye. Okay, so that doesn't happen because our pupil is so small, something about 5 millimeter to 7 millimeter. So now, is there a way to expand our pupil so that we can see more faint stars or maybe faint nebula, faint galaxy? So that is here why we need a telescope. Okay, so because we cannot actually expand our pupil beyond this size. So without doing any surgery to our eye to expand our pupil, what is the method that we do have for that? So for that, I am taking an analogy, something like this. Imagine that there is a bottle and you are supposed to collect rain uh, in this. Okay, so and you are on an open ground. Okay, so the problem is that the rain can only enter through this tiny hole. Okay, you can see that tiny hole, that is the only available area through which available cross section through which the rain can enter. So it will take a long time. So suppose that if I am giving you 5 minutes, sure, it won't get full. Okay, even if it is a heavy rain, within 5 minutes it won't get full. But if you use something like this, what is called a funnel, you can actually easily fill it in within some 5 to 10 minutes. Okay, so here what is happening? So even though your bottle's opening is small, this funnel allows it to expand so that all the rain falling in this larger area will be converged or focused or narrowed to this small opening so that we can get sorry, so that we can uh, collect rain so easily. Okay, so this is a similar problem that we are having. Our eyes opening is so small, so do we have a funnel? So something, our eyes opening is so small to some millimeters, so shall I place a funnel like this? Anyway, for sure, as you know that it's a funny picture, something like it won't work anyway, because as you know, this is a tiny opening, or this funnel won't apply for light. So even if you shine a torch, that light won't get focused to this point. So we need something to focus light to a specific point. So there are two kind of optical instruments are there which is able to focus light to a point. So I will give the first example. You can see if you take a magnifying glass, that is basically a convex lens. Okay, and if you try to focus sunlight, not to your eye, okay, to a dry leaf or some paper or a match stick or something like that, know that within some few seconds, that place where it is focused will starts to burn. Why it is happening? The light is falling on this one side, will be focused to the other side. So that focusing is actually what is happening. So actually a convex lens is working like a funnel. So now imagine you are placing your eye here, okay, while focusing towards the sun, or while the lens is towards the sun. So then you can imagine, so it can burn a paper, means then imagine about the soft tissue in your eye. So that is why it is always said that using a lens or a telescope which is made using lens is not advisable, or never point that way, uh, uh, point that to sun, or even to bright light. Okay, so it is not good for our eye. Okay, so that is why it is said, so if it can burn a paper, then your eye is nothing for it. Okay, so that is one thing. Now let's go, but we can actually use the telescope to see other faint things in the night sky, so that's not a problem. Even the moon we can use. So for that we have a convex lens. So the convex lens has the ability for focusing light to a point, and this is a convex lens, and you can see that from this center of the lens to the point where the light is getting focused, that distance is called the focal length of the telescope. Oh, sorry, focal length of that lens. Okay, so this distance is called the focal length. Just note down that, or just understand that distance. Okay, now we can make actually telescopes using this. So before going to that, let's analyze what is the importance of this focus point. So here you can see I'm just giving you an equation without derivation. Okay, so this you will maybe in your higher classes you will learn the derivation and all, but I'm not going to explain the derivation here. So lenses actually working on the principle of something called a refraction. Okay, so some principle called a refraction is there. So when light passes from one medium to another, there will be a bend at the separation of the media. So that is what is basically called the refraction. And based on that, there is something called a refractive index is there for each object and all. Okay, fine. So anyway, now here you can consider a convex lens, and it has a focal length. So we are making an equation to find the focal length. So just leave lambda right now. You can see that 1 by focal length is equal to n lambda. This lambda has an importance. I will explain it later. And minus 1 into 1 by r1 plus 1 by r2. Let me explain what is this r1 and r2. So any convex lens can be considered as a combination of two circles. Actually, it is not circles, two sphere. Okay, there is one sphere and there is another sphere. So the radius of the first surface. So for this surface, the right surface, there is a sphere, and that radius is called r1. For the other one, there is another. Okay, that radius is called radius of curvature, that is called the r2. These are all the r1 and r2. So we can imagine a lens as the combination of two spheres. Okay, and the radius of each of them, is are called the radii of curvature. Okay, now n lambda, n is called the refractive index. Anyway, this equation won't be there for your exam, don't worry, but this is to explain something. You can see there is a lambda here, f lambda and n lambda. So what is the importance of this lambda? Lambda means basically wavelength of light. So the focal length, so the light where it to be focused depends on, okay, it depends on where, what kind of color it is, or what is the wavelength of light. So when a red light is coming through this, the focal length is some point, and when the green is coming, the focal length will be somewhere over here. That means all the different colors that are coming won't be focused to the same point. It has a problem with the lenses that we will discuss soon in the coming slides. So just understand from this slide what is your takeaway. So when you take the equation for the focal length of lens, it depends on the wavelength which we use. So wavelength means simply you can understand as what kind of light, something like whether it is a green light or yellow light or blue or green, whatever it is. Okay, so that's it. Now let's go and make the telescope, then see what is the problem with this equation, or what is the issue that is coming because of this equation. Okay, so for that we can make a refracting telescope, because lens works on the principle of refraction. That is why it is called the refracting telescope, and usually it is also called a refractor. Okay, sometimes instead of writing it as refracting telescope, we can write it as refractor as well. Okay. Okay, that is also another single name we can use instead of this reflecting telescope. And it has two lenses. So why we need two lenses instead of already we know that a single lens can focus light to a point. Okay, something like this. I am taking that single big lens. Okay, and it can get the light falling and it can focus. Why can't I place my eye here? Okay, instead of having a second lens. So the problem is that if you try to place your eye something like this you can actually do with a lens and maybe focusing to moon or something. If you try to place your eye here, the light won't get focused. So to focus that light to your retina, you need to make the light coming from here or coming here should be made parallel like this. So we can put a second lens here, and the second lens will make these lines parallel, so that now if we place our eye here, okay, your eye here, this eye can actually focus this light. So that is how this is working. So that is how a refracting telescope need a second eyepiece if you want to look through them. Okay, so this is how it is. So here we use two lens. One is the objective. Objective will be the lens which is towards the object. That is why the name objective, and eyepiece is the lens through which we are looking with our eye. That is called the eyepiece. And for professional telescopes like the Kick telescope or maybe the Hubble Space Telescope, whatever kind of professional telescopes in the sense that is used for scientific imaging and astronomical or astrophysical studies, for those telescopes they usually won't have this eyepiece. Instead of this eyepiece there will be a camera here. Camera in the sense that a camera sensor will be placed here and the image will be directly recorded without even using an eyepiece. Okay, so that is just for your knowledge. And one more thing, so based on this objective, the objective is the main lens which collects all the light. So bigger this objective, bigger in the sense, bigger in the size. Okay, if the diameter of that lens is so large so that it can collect more light, means the brighter will be your image. Okay, so that is why we need bigger. That is one of the reasons why we need bigger telescope. If you compare it with our analogy of what is called the that funnel, you can see that if it is a small funnel, okay, it can get only a tiny amount of water. So if I make a bigger funnel, something like this, it can collect more water. So that is the simple idea. Okay, so it is something we can actually compare these two and say that it is like this. So that is why we need bigger and bigger lenses. Okay, now let's see how to calculate the magnification of a telescope. Okay, so how much it is magnified. You can see that for that you have to divide two numbers. The first number in the numerator is the focal length of the objective, and the second number is the focal length of the eyepiece. For example, let's take objective focal length is some uh, let's say some some 60 centimeter, and the eyepiece focal length, let's say it is 5 centimeter. Okay, then we can divide it. So if you substitute that in this equation, 60 centimeter divided by 5 centimeters meter, which is equal to 12x, is the magnification. Okay, now you can see one more thing. So for making the for improving the magnification, either you can increase the change the objective lens, but it is always easier to change the eyepiece. So instead of that, if I use a 2 centimeter eyepiece, what will happen? This becomes 30 times magnified. So you may think that if I use a 1 centimeter, I can get 60 times. So what if it is a 0.5 centimeter eyepiece? Then I can get 0.5, then it is 120 times. So you might think that it is something like I can get infinite amount of magnification just with a single telescope. The problem is that you can magnify this maybe in theory, but the problem is that when you do that, the whole light that is coming from this lens is being magnified. So as you magnify more and more, the object becomes less visible, or it becomes less brighter and brighter, and finally after a certain limit it becomes useless to magnify. So magnification is not that important, especially in the case of all the professional telescopes. They use a what is called a sensor here, okay, something like a sensor that is there in your camera, but it is a bit different. This is called a CCD sensor, so that CCD will directly record the light that is coming. So that's about it. Now there are two different designs for the generally refracting telescope. Something like you can either use a secondary lens as the eyepiece. You can use either a convex lens or a concave lens, or maybe a plano concave. It is called a plano concave because one side is plane, other side is concave, so it is called a plan concave. Okay, and there is many other kind of lens combination. This is actually called a double concave. So this is called or biconcave, or this is called a convex or biconvex because both sides are convex. This is called a plano convex. So depending on it, we can call it as different. If you just leave it. So I was just explaining what are the different types of combination of lens. Or types of lenses. Anyway, generally, if you use a second lens or the eyepiece is a concave, then it is called a Galilean telescope because this is the telescope that is used by Galileo, and this is called the Kepler telescope. This is another design where the eyepiece is a convex lens. So this is what we usually familiar while making simple one using the available things and all. So now let's see. What is the issue with this kind of refractor telescope? So when you look at the refractor telescope, the first issue I will explain this one, okay, chromatic aberration. So if you remember the equation for focal length, the equation was something like 1 by f lambda. If you remember the lambda, then it is something like n lambda minus 1 into that something that is 1 by r1. That equation was there. Okay, so you know that. Okay, here you can see that the focal length depends on color of light. Here you can see that the red, blue and green is coming. Here also red, blue and green is coming. It is supposed to focus at the same point, but the problem is the red is being focused here. The blue is being focused here, the green in between. So that is an issue with the usual lens, which because of that, if you make a telescope using lens and look at some objects, then the problem is that you see some colorations here. So this is not the actual colors from that object. This is actually happening because of something called the chromatic aberration. Okay, so that chromatic aberration is a serious issue with the telescope. But there are some other kind of lenses. They are called a achromatic doublet. Okay. So to compensate for this change, we can actually add an additional lens along with this. It's a combination of two lenses. Okay, we call it as a doublet. Okay, so that actually we can avoid this chromatic aberration to a limit. Okay, so that is called a achromatic doublet. Now there is one more issue that is called the spherical aberration. Here you can see that the focusing of the light rays that is coming through the center. Okay, you can see coming near the center, or we call it as the near axial. Okay, axial, we call it as axial rays will be focused somewhere over here, and far away from axis, or the light that is coming through the or passing through the edge of the lens will be focused somewhere else. So this happens for any focal length. Okay. So what is the problem with that? That is why when you are observing through a lens, especially just take a magnifying glass and see some letters on a paper or something like that, the center part will be sharply focused and the side will be blurred. So this is because of this aberration called a spherical aberration. So this spherical aberration and chromatic aberration is a major issue for a lens telescope. And now there are some other telescope issues. So we want to make bigger and bigger telescopes, so that we have to make bigger and bigger lenses. So in the case of a lens, the issue is that it has two surfaces, one here, one here. So both the surface should be polished well and made well in the proper curvature and all. And when we fix this to a pipe or something, pipe in the sense not a small one, if you want to make big one, we need a bigger pipes. Then the problem is that you can only connect, you get support only at the edges. So only that edge of the lens can be hauled with that mechanical construction, or maybe that pipe basically. So that is an issue. That is one problem. So if you want to make heavy lenses, it is actually difficult to construct, and heavier glass pieces are, or heavy, bigger the lens, it will be heavier as well. So it is, we cannot go beyond a limit. So that is a limitation basically for this kind of lenses. So that is why we have another kind of light focusing technique, which is using mirrors. So these are called concave mirrors or converging mirrors. It has the ability to converge light to a point. Okay, something like the light can get focused to this point. Okay, so again, something can focus the light, then we can use it as a to use it to construct a telescope. So one method of construction, and here one more example, I will give you another equation. Again, here you can see that F is equal to R by 2. So R means this image or this mirror can be considered as the part of a big circle or maybe a sphere. Okay, and the radius of that sphere is called a it will be so big one. Okay, it will be something like this. The center will be somewhere over here. Okay, I'm not drawing it anyway. I hope you got the idea. So this can be considered as the part of a sphere, and the radius of that sphere is called r. So r by 2 is the focal length. Here you can see that simply there is no lambda here. Okay, what is the meaning of that? Because the focal length of a mirror doesn't have anything like the wavelength. That means whether it is a blue light or whether it is a red light or whether it is a green light, all the light will be focused to the same point. So that issue of chromatic aberration is solved. Also, the mirrors doesn't have that spherical aberration as well, so that it is easy to avoid both those aberrations for this mirrors. Now we got mirror doesn't have spherical aberration and chromatic aberration. Now let's try to make a telescope using that. Okay, so for that I am taking a pipe and placing a concave mirror here, and now imagine the light is coming in this direction and it is getting focused. Now I am trying to place, even for this, here you can see the light is being pointed here or maybe converging here. You cannot place your eye here. You need a second lens that is called eyepiece here, so that this become parallel and you can observe. So what is the problem? If you come with your eye, okay, and place it here, what will happen? You can see that problem is that if this is my eye, my head will be this big. Okay, just imagine. Okay, so once I place my head in front of the telescope, I am once again blocking the light coming from the suppose I am observing Saturn, the light from the Saturn will be blocked by my head. So that is a problem. Okay, so I cannot place like this. So that is one issue with this kind of telescope. So the idea is that let's do another clever idea, okay, that is actually proposed by Newton and made by Newton and actually invented by Newton. You can see that we place a small tiny flat mirror here. So what will happen? Yeah, this mirror will reflect the light upward. Okay, so that I can place a lens safely here and I can actually observe it from here. So it doesn't. But this mirror, this tiny mirror will block a small part of the light that is coming from the Saturn. Maybe this center line will be blocked, but that is fine. Okay, apart from that, there is nothing will happen. That won't be a problem. It will decrease the brightness a bit, but anyway still we can observe it easily. So when compared with the size of the main mirror, so this is called the primary mirror. This secondary mirror, this is called the secondary mirror, is so tiny so that it won't block much amount of light. Okay, so that is how the reflecting telescopes are working. Especially this design is called Newtonian design. Okay, now let's see another, so the top one here, you can see that the same one, another diagram, that's all. This is getting reflected here, and you can see this. Okay, so here you can see that if you take this, this is called the Newtonian design. Okay, because the light is getting reflected with a plane mirror to a side. Okay, so this is called the Newtonian one, and this one is called a Cassegrain. So here the idea is bit different. Okay, so the light is coming from here and reflecting, and it is supposed to focus here like the same above. Okay, but here what will happen, that same light will be reflected back using not a flat mirror. See, this is not a flat mirror, this is a curved mirror, and this curved mirror will reflect back the light to the same mirror. But what is the problem here? It was the mirror. Now we put a small hole at the center of the mirror, and that light will pass to the back side of the telescope, where you can place eyepiece, maybe camera, or whatever you need. So this is called a Cassegrain telescope. And now there are another kind of design called a Ritchie-Chrétien telescope, Schmidt-Cassegrain telescope. These are all the modification of basically this concept. And based on what kind of mirror it is, maybe this can be a shape of a parabola, so, or hyperbola. These are all different kind of curves. So the curves can be many type. It can be elliptical, it can something like an oval, maybe a circle, and there are some other called parabola, hyperbola, etc. So based on that shape, the design name will be different. So anyway, broadly we can call it as a Cassegrain design. That's all. Okay. So minor or major improvisations are there, but the concept is almost the same. Okay, so that is about the reflecting telescopes, because it works on the principle of reflection, or sometimes in short we call it as a reflector. Okay, so that is about the reflecting telescopes. Now the next thing, so we need bigger and bigger telescopes. So to make bigger and bigger telescope, it is always better to use mirror. One reason is that it is devoid of what is called the chromatic aberration and the spherical aberration. Second thing, for a mirror, we can neglect the back side. So the back side of the mirror, whether it is looks like some scratchy like this, or maybe flat, or it is not polished, it doesn't matter actually. What matter is only this reflecting side. So there is no need to take care for the both side like that of a lens. We have to take care only one side. The second thing, so since it is the back side is not at all used, we can actually support that mirror using a proper mechanical structure. Even if it is heavier, we can actually give a proper hold at the back side. So that is the use of the second surface. Okay, so that is why to make bigger and bigger telescope, we use always the reflecting telescopes. Okay, now there is one more reason. So one reason for making big telescope is to collect more light, something like the analogy of the what is called the funnel. Okay, so similarly, like a funnel, we make bigger and bigger funnels, or maybe bigger telescope, to collect more light. Okay, now there is one more other reason other than just simply to get more brighter. Other than that, there is one more reason is there, that is about something called the resolution. So before going to resolution, let's see, whenever you see some object in the night sky, or even in the sky, the two, if you draw two lines from the two edges of that object, so you can, this is your eye, you can draw two lines from the two edges, so that it will make an angle. Okay, that angle is called the angular diameter. Okay, or angular size of that object. So the sun is something around half a degree. Okay, it is around half degree. So if you take two stars, for example, okay, and if it is so far away, it will make a large angle. So we can say that they are at a high angular separation. Or if two stars are so tiny, okay, something like the Mizar and Alcor, they will make a tiny space, a tiny angle, even less than half a degree. Okay, so it is so tiny. So that is about the angular separation. So what is the importance of this? So in a telescope, when you see through the telescope, maybe some stars, if you look directly, it will look like a single star. Okay. One best example is Alberio. If you know this, I don't know whether you know. This is in a, I forget the constellation name. So there is a star called Alberio. So Alberio, if you look with your eye, is actually a single star. But if you look through a telescope, you will see it as two different stars. Okay, so they are so close by. So an optical instrument has the ability to resolve or separate out these close by objects are two objects. That ability of an optical instrument is called the resolution or resolving power. Okay, so just leave that. Okay, you can see here, suppose if you have two close by stars, okay, if you look through a telescope, maybe in a telescope with a low resolution, it will appear as a single object like this. Okay, single star. But if you look through a high resolving power telescope or high RPA telescope, then you will see it as two separate dots. Okay, so that is called the resolving power, and that is measured using this equation. Theta is equal to 1.22 lambda by d, where lambda is the wavelength at which you are observing, something like whether it is infrared or maybe visible or whatever, then wavelength. So just leave the wavelength, since assume that we are observing the visible light, and theta means that is the minimum angular separation which we can see. Okay, so, or in other simple means, we can say that theta is smaller, then it's a better telescope, or better resolving power. Better resolving power. Okay, so that is the concept. So theta should be smaller. So for theta to be small, either lambda should be larger. So we are fixing the lambda. Then what is the idea? There is something in the denominator, that is d. So the d should be larger. So d means, what is the d? That is the diameter of the mirror or diameter of the lens. So that is why if you make a bigger telescope or big telescope with a bigger lens or mirror, then you get better resolving power. So for resolving power as well, we need bigger telescopes. Okay, so that is called the, and this equation is called the Rayleigh's criterion. Just leave that, you just understand that name, that's all. Not explaining that equation. Anyway, from this equation we can infer that not just for getting a brighter image, but also for getting a good resolving power, or to resolve two close by objects, we need larger telescope. So that is why astronomers are always trying to build larger and larger telescopes. And now, yeah, now one more thing about the telescope, that is called a mount. Okay, so I won't be describing more about it because it is okay. But anyway, I will give you just a brief idea. So two types of mounts are there. Mounts means the telescope cannot be fixed on a something like a concrete pipe or something like on a metal pipe. We cannot fix the telescope because the telescope has to be moved, maybe to move from one object to another, or even if you are tracking an object, because all the objects in the sky is actually moving. So if you are observing moon or maybe Saturn or some other galaxy, so the galaxy is actually moving through the sky because of the rotation of earth. Okay, so due to that rotation, if you want to see that galaxy always in your field of view, always in your field of view, then okay, always in your field of view, then uh, that telescope should be moved along with that object. So we cannot fix a telescope. So that is why we need a movable system, so that it can move to any other desired location or to track things. So for a altazimuth mount, you can see that it is something like a camera tripod. It can actually pan like this. Maybe you can rotate like this, north, south, west, east, something like that. And also it can actually move from height, actually, something like maybe when it is pointing towards here, it is actually pointing towards the horizon, and you can make it higher and higher so that it can come even vertically so that it can see the mid sky, or what is just about this point above the, when there is a point when you are standing like this, and the sky is here, the point just above your head is called zenith. Okay, so this is the zenith. So if you, even if you want to rotate it to zenith, it is possible with this kind of mounts. So that is the purpose of mount, so that we can move the telescope to anywhere. So the simple kind of mount is called alt azimuth, where the movement is so simple, something like a camera mount. Okay. Now there is one more kind of mount, which is called an equatorial mount, where you can see it is a bit complicated in the sense you can see that one axis is actually always pointing towards the what is called a pole star. Okay, or this axis is always parallel to Earth's rotation axis. And now the telescope can actually rotate. So this is to Polaris about this axis and about this axis. So there will be two movements. Okay, one will be north south, and other will be something like east west in the sky. So we can call it as in right ascension and declination there will be two movements. So why we need this complicated mount? Okay, when we have the simplest one that you have seen in the previous one. So the advantage of this one is that, so if you want to track an object, actually this telescope can easily track just with the use of a single motor. So the telescope, especially all the professional telescopes, are actually powered by machines. It is not moved manually. So that when you are tracking an object, you have to only work a single motor. So that you can get more precise and accurate movement. So that is why they use equatorial mounts. Okay, so that is another reason. Astrophotography as well, we use equatorial mounts. Okay, so that's about the mounts. Now I will just skip through or go through some uh, two or three famous observatory, just giving you a glimpse. So but in this thing, I'm suggesting you to read more about other telescopes that are available. Okay. Okay. Now, the first one is X Observatory, and the location and everything you know how to read. So one thing, that is altitude is there. That is the height at which the telescope is placed. So Earth's observatory is relatively at a lower altitude. It is only some 334. But as you go to another observatory, we will see that it is usually above some 2000 meter. It is always placed on a, sometimes on the top of a mountain, because to avoid the many thick part of the atmosphere, so we will get avoided by many uh, part of the layers of, not the complete layers anyway, some thick part of the ground layers of atmosphere will be crossed, so that we get a less air dense space there. Then another thing, it will be less humid and less light polluted. Now you can see that here about the, what are the telescopes there. One telescopes in X observatory is 40 inch. So what do you mean by 40 inch? 40 inch means, is it the magnification, is it the focal length, or is it the size? So whenever you hear something like this, uh, only a single number, that means that is actually the size of the telescope. That means the diameter of the primary thing. That primary means it can be either a mirror or a lens. And if it is written as a refractor, that means it is for sure it is a refracting telescope. And here in the same observatory, they have another 14-inch reflector as well. Okay, so this is one of the older one. Now I think it is not used for any professional observation. It is something like a museum or something. This 40-inch is being used, I think, but this refractor is something they kept as a uh, yeah, it is kept as a museum. Now this is called a large binocular telescope. You can see two mirrors are there. Okay, two single mirrors you can see, but it works as a two different mirrors. But the images from both this telescope will be combined into a single image. It is something like a binocular itself. So it is called a large binocular. Here, see the altitude at which it is placed, 3221. Okay, and you can see another value here, the first light. First light means this is the date at which the telescope got a perfect image, or it used for imaging. It is not the date of inauguration or anything. It is, so when we make something, we will try to test it. So whenever we get the first proper image, that date is called the first light of the telescope. And you can see the diameter 8.4. Optical telescope, that means it mostly observe in the visible wavelength. Okay, and mirror we are not actually specifying, because already we know that this is a reflecting telescope. So anyway, now another one, focal length, that also you can see. Then mounting, what kind of mount? It is an alt-azimuth mount. Okay, now this is the Gran Telescopia Canaries, that is in Spain. You can see that it's a 2000 and Ritchie Chrétien design, and you can see that this is a segmented mirror. So what do you mean by a segmented mirror? You can see that this is not a single mirror, single entire mirror. A big mirror is made using tiny pieces of mirror, something like the JWST design. Okay, this is called a segmented mirror. But at the same time, if you look at this, this is not a segmented mirror. This is called a monolithic mirror. Okay. So the single mirror is usually called monolithic mirror, and this is called a segmented mirror. Okay, you can see the diameter is 10.4. So instead of making a single 10.4 meter mirror, they actually made it into tiny segments and made it into a single mirror. Okay, so this is another one, Keck Observatory. Each of this is called a Keck Observatory, and this is called the Keck twin telescopes. Okay, identical telescopes are there in both of them, and they are actually observing separately, not to the same location. And you can see that it is 4000 meter above high, and its size is 10 meter. So both of them consist of, here a 10-meter telescope is there, here a 10-meter, and they are actually segmented mirrors. Okay, now this is another interesting telescope where I worked actually, that is called the International Liquid Mirror Telescope. So as I mentioned, even though mirror telescopes are better and easier to make when compared with the lens telescope, but even though the mirror is actually not that easy to being built, so it has to follow. We have to get a rough sketch from the some cast of mirror, sorry, glass. Then it should be polished. It should be even polished to the size of a something like a nanometer level. It has to be polished. Then it has to be coated with the aluminum or any other reflecting metal, and we will coat with that, and that is being used as the mirror. And the building process will take almost 6 months to 1 year for a mirror, and it will take it need a lot of money and effort and time. So that is why those telescopes are so costly. Now this is another cheap and effective method of making telescope, that is called liquid mirrors. So instead of making a single solid mirror, they take a ball full of, I will take a 2 minute to explain this, and I will wind up, then I will take the questions. Okay, so it will be something like, this is the side view, okay, where this is a ball, and this ball will be filled with mercury. So as you know, mercury is a shiny metal, a reflecting liquid. So it is a metal. Metal is not that important here, but it is a shiny metal. Okay, it is a reflecting liquid. So when that liquid is filled in this thing, and when we rotate it, okay, something like this, you can see. Okay, when we rotate it, the liquid inside that will assume a shape of something like a curve, something like a concave surface. So why this is happening? Because of the centrifugal force that is being acted outward, and because of the gravity downward. So as a resultant, there will be a shape like this, and this shape is that of a concave mirror, and this surface is actually concave, and it is reflecting. so that it can focus light to a point and where we can place the camera, and this can act as a mirror of a telescope. So that is what you're seeing here, and this is called the liquid mirror telescope. This is one of a unique kind actually, and this is the only one that is currently operational for astronomical purpose. That is in India. Okay, I will show you. That is in Devastal, Uttarakhand. Okay, that is in India. Forgot to add the name India. Sorry. And that is an international collaboration with some universities in Europe and India actually. Okay. So its primary mirror is 4 meter in size. Okay, it is being rotated, and 60 50 kilogram of mercury is being used, and it is keep on rotating. So the advantage of this kind of telescope is that it is so cheap, sometimes even 1 by 10 the cost of the same kind of a solid mirror usual telescope. Okay, but the disadvantage is that since it is keep on rotating and the gravity is the main reason why it is having the shape like this, if you try to tilt this telescope to something like this angle, either the mercury will spill over, even if the edges can be made larger because of gravity, this curvature will be always like this. Okay, even if you change the orientation, so, the curvature of the mercury will be always pointing towards the zenith point. So exactly to the mid sky. So this telescope cannot be tilted, or it cannot move to a targeted object. So if I want to see Saturn, which is near the horizon, I cannot tilt it. If it comes to the straight point above, then I can see. That is the problem with this kind of telescope. It is not steerable, or it cannot be moved. So whatever comes to the head of the telescope or head of head, that will be observed. That's all. Okay, but it has some other special usages, something like it can be used for surveys and all. So it is also useful, and this is a unique kind of telescope. So that's about it. And here a short picture of different size of telescope. You can see this honeycomb designs are segmented mirrors, and the single colored ones are or what is called the monolithic. So here you can see the size of a human, and this one is what we mentioned, like the Grand Telescopia Canaris is here, Keck telescope is there, large binocular telescope is there. Then you can see, yeah, this is the Yerkes Observatory. See, that is here, and JWST is here, Hubble Space Telescope. Then some of them are actually on maybe planned for 2027, maybe 29 and all. These are all not running right now, and there are some cancelled ones maybe. 30-meter telescope is I think it's on construction, it is happening. So that is about it. Now we will go for radio telescopes and space telescope, X-ray telescope, etc. tomorrow.